Good morning to all. This is Anvesh from Triple E branch, and today my topic is about multi-quantum well laser for telecommunication. Mm, Yes, yes, multi-quantum well show unique properties that ample explosion of the optical fiber potential for the telecommunications. And it is invented in the 60s. The semiconductor laser diode has made practicable theoretically boundless bandwidth of optical fibers following the initial AIGS based sources emitting near 850 nanometer wavelength. Quaternary compounds of InGaps allows grown on INP have been introduced to explode the wavelength region first around 1300 nanometer and second around 1500 nanometer where fiber attenuation is the minimal to data semiconductor laser are installed in undersea optical transmission links intercity and inter-office system distribution networks and optical interconnections between computers equipment and even inside electronic circuits combining well with multi-favors requirements. More recently, although it was invented in 1976, the multi-quantum well laser based on few monolasers thick active material has come to practice thanks to the maturity of epitaxial growth techniques. The new structure has immediately resulted in remarkable performance improvements. Moreover, this future degrees of freedom in material preparations is offering unprecedented opportunities to device engineer in the conception of novel sources. The aim of the article is to show how MQM laser can effectively match as well as forecast a variety of telecommunications need ranging from high performance fiber optic transmission system to very low cost application by exploiting the environment's flexibility and the peculiar physical properties of these artificial materials. After a description of fiber optic transmission requirements, we will analyze in detail the operational and physical properties of semiconductor lasers in order to point out where MQWS play their major role. The state of the art for these devices will be illustrated with a discussion of experimental characteristics. Now we'll look on light wave telecommunication requirements. In order to face the many challenges of future telecommunication networks, new improved optical transmitters are currently being investigated. Performances are required for high capacity and long span transmission systems. Although laser sources are already commercially available for bit rates in excess of 2 Gbps, typically 2.488 GBITs for SONET specifications. Many laboratories are investigating practically transmitters operating at higher speed. The flexibility of a 10 GBITS transmission system has been already demonstrated, and many Research efforts are focused on finding the laser structures exhibiting the largest optical bandwidth. However, for high transmission speeds and long distance, the optical spectrum of a laser diode is of great importance because of fiber chromatic dispersion appearing in the 1.55 pm region. In fact, after several kilometers of conventional fibers, the different wavelengths contained in the light pulses carrying information have propagated at different speeds, so that optical signals are destroyed, and intersymbol interference can severely limit the receiver sensitive effect of dispersion has been overcome with the disturbed feedback laser structure demonstrated in the 80s for long wavelength operation and currently manufactured. The internal structure of the source selectively allows a single longitudinal mode to oscillate, producing a very narrow spectrum. However, some excess spectral boarding arises due to the large modulation current applied to the laser diode. This is so called chip can amount up to several nanometers in conventional def laser, and thus it is strongly affected the span of dispersion limited transmission systems. The availability of zero chip sources is an outstanding challenge for the future availability of signal single frequency sources has also encouraged a more efficient use of fiber bandwidth, adopting frequency division multiplexing FDM techniques to transmit simulation simultaneously many channels on the same physical carriers. The highest density corresponding to the several hundred channels spaced by only 1 to 10 hexabyte hazard, roughly 0.01 to 0.1 nanometer in wavelength, could be obtained with correct detection based on optical heterodyne by the technique. Optical signal are mixed in the receiver with a single frequency emission of a tunable laser used as a local oscillator, thus allowing channel selections. So this is the diagram of the telecommunications. You can see and you can observe the electrons over there. There are p type and n type, and there is a metal contractor between them and carrier conformants. And this detection scheme implies a high coherence of the light produced by the transmitter and the local oscillator, which is usually quantified in the terms of spectral line width, as well be shown subs- uh, subsequ- subsequently. Extremely narrow line width source have been made possible by DFB structure based on MQW materials. Although the need of all local oscillator operating in the all a large tuning range with low line width is not yet satisfied. More recently, there has been an increasing demand for cheap, fast, and ridge transmitters operating at very low driving current with a low sensitive to temperatures. These lasers are very suitable as light sources for subscriber systems or in interconnect application to transmit data streams on a fiber cable. as well be seen the high level of performances achieved with MQW material also allows most of the requirements of this application to be met. Now, coming to conclusion, over several years, now a considerable part of the F progress in semiconductor laser has to be attributed to the use of MQWs in their technology. Most interest of MQW in modifying the physical properties related to the light emission and all the affected parameters have the great advantages of varying in a direction favorable for performance improvement. Then the comparable to bulk laser optically gain per injected carriers in higher and optically loss inside the cavity and non-radiative recommendation rate become lower. One main drawback MQWS could be their fabrication complexity, but recent progress in epitaxial technology lead to be very confident in the availability of MQW laser as very rich, uniform and reproducible MQW materials can now be grown by MC, MOCVD, MBE or CBE techniques on 2-inch wafers. As shown in the article, MQW are very profitable for both statics and dynamic laser properties. Lower threshold current, high maximum operating temperatures, and higher power confer- conversion efficiency are definitely desirable for fabric optic transmitters, but have also become up become of prime importance for the fabrication of high performance pump sources for optical amplifiers, as well as for the realization of lower cost 1.3 or 1.5 millimeter emitters. On the other hand, spectral purity improvement in the continuous and plused operation of MQW DFB laser are relevantly to take profit by the huge optical fiber bandwidth with a CMC technique and to avoid fiber dispersion problems in high bit rate long distance links. The additional degrees of freedom available for design will be essential to extend the optical bandwidth limit of present laser as well as conceive new structures exhibiting a quasi zero chip under current modulation. All these expected performance will allow the best of optical fiber technology to become exploited in the future. And now coming to acknowledgement. The authors wish to acknowledge the help of C. Kazimierz D. Mathurizing and N. Buedmet for providing some experimental data and figures. Now, these are the reference books you can read, you can refer from these books, and you'll know more about multi quantum well laser telecommunications. So, anyone book, but mainly I refer the third one. Now, coming to biographies. Jean Claude Boole received his doctorate degree in solid state physics from the University of Caen, France, 1972. From 1970 to 1973, he worked at the Optoelectronic Laboratory of LA Radiotechnic, where he was involved in the research of gas lighting emitting diode. He joined Scent's laboratory in 1973, where he was first engaged in Zen's LEDs. Since 1975, he has carried out several studies on technology and characterization of laser for optical communication. He presently head the Optic Electronics and Materials division of France Telecommunication, which is engaged on district and integrated optical sources for low cost, high speed, and multi wavelength applications. Giovanni Destanis was graduated with a degree in physics in 1969 at the University of Turin, Italy, with CS Linton since 1970. The Corporate Telecommunication Research Center, Bagnax, France, of the STET Group in Italy. He initially did applied research on the film and magnetic bubble memories and the characterizations of IL-V materials from 1981 to 1992. He supervised the design, processing, and characterization of in-phased optoelectronic components. He has been ceaselessly responsible in national and international projects in optical optolerance and integrated optics and currently. And thank you for giving this opportunity. I hope all you have understand my PPT.